Well, hello class. Alright, well, it turns out that since we know that the gradient vector del f of x, y, z is normal to the surface f of x, y, z equals 0, that allows us an easy way to solve some different geometry problems in three-dimensional space. For example, find the symmetric equations of a tangent line to the curve of intersection of the surfaces in R cubed that are given below at the point x is 2, y is -1, z is 5. And also find the cosine of the angle between the gradient vectors at that point. So by the way, of course, that's finding the angle between the tangent planes at that point, or you could even say the angle between the surfaces at that point. So state whether or not the surfaces are orthogonal at the point of intersection. Okay, so we'll find out what that angle is, and then we'll know that answer. So one of the surfaces is z equals x squared plus y squared. The other one, by the way, that's a paraboloid. The other one is z equals 4 minus y, which is just a plane. So we've got these two functions, and del f for this one, 2xi plus 2yj. Del g for this one, we'll call it del g, I guess, is just negative j minus k. Oh, I forgot about the minus k on this one. Remember, the z coefficient is always -1, so -1k. And del g, same thing, -1y, so -1 is the derivative, so negative j minus k. And so we've got our two vectors, and the cross product of these vectors will give the direction numbers of the required tangent line. Stop and think about why that's so. The cross product of two vectors geometrically, the length of it is the area of the spanned parallelogram, and the direction is orthogonal to the two vectors. So we'll get our orthogonal direction numbers for the tangent line. And so we just evaluate this determinant, and I admit I use my software to do this, but you should know how to do this. I times 2 minus 1, so 1i. Negative j times -4 minus 0, so plus 4j, so you see why it's plus, there's two negatives in that. And then plus k times -4 minus 0, so minus 4k. So we got our direction numbers, 1, +4, and -4. And we know our point was the point x is 2, y is -1, z is 5. So we should be able to find the symmetric equations of the tangent line. Keep in mind, partly that's from the point 2, -1, 5. See? Where we use the 2 here, the -1 here, and the 5 here. And the direction numbers, which came from this cross product, 1, 4, and -4, and there they are in the denominator. So that's the symmetric form. I didn't say anything about the parametric form, but that would be something like x equals 2 plus t, y equals 4t minus 1, and z equals -4t plus 5, or 5 minus 4t, something like that. Anyway, here are the two surfaces, and this one I can rotate, but at the point x is 2, y is -1, here's x2, here's y is -1, and z is 5, that would be somewhere around here. We can find the tangent line to the intersection of those curves. And so that's what we did, as a matter of fact. And here is the equation of that tangent line. Well, we found the equation of the tangent line, and there it is drawn in purple. And we also know the cosine of that angle is del f dot with del g at that particular point over the length of del f times the length of del g, and now we may need to go back for those things. Here's del f, here's del g. Maybe I'll copy those, bring them down where we're finding that. The length of del f at the point where x is 2, y is -1, and z was 5. So if x is 2, that means 4i. Y is -1, so minus 2j minus k, and that would be the square root of, well, actually, let me dot them first. The length of it, I'll work that out in a little bit, but that would be the square root of, let's see, 4 minus 2 and 1, so 16, 20, square root of 21, and times, actually it's easy to figure this one, times square root of 2. Square root of 21 times square root of 2 is square root of 42. That was easy. Now, the del f dot del g, I haven't done that yet, so don't forget that x is 2, but when we dot that with this, the i's come out to 0, because this is 0i here. So then we're also going to have, now y is -1, so that makes this -2 dot with this -1, which gives us a 2, and then this k, both with -1 coefficients, so that comes out to 2 plus 1, so 3 divided by the square root of 42. And no, they are not orthogonal at the intersection point. If they were orthogonal, what would the cosine of this angle be? Of course you know. It would be 0, because then the angle between them would be pi over 2.